Thank you so much. Could you confirm that you can hear me? Yes?
Yes, sir,
Yes,
you are
sir.
audible, sir.
Perfect. Now I will share my screen. Give me a second, please. This is Google. Okay, yeah. Entire screen. Yes, my secondary screen. And could you see my screen right now, isn't it? Could you confirm that you can see my screen, please?
Yes, sir, now we can see your
Yes, sir.
screen.
Perfect. Well, very good morning to everyone, or very good afternoon, depending where you are located. Thank you very much for this invitation to be part of this sustainable development and recent advance in electrical engineering. It's my pleasure to be here, and thank you very much for your very kind words. I really appreciate the extensive introduction and the very kind words. And let me see something here that is ringing. Okay, what I would like to start today is I will share some of my experiences using digital real-time simulation. And the reason that I want to share these experiences is because we are in a very fast transition in the electrical power systems. In the previous 5 to 10 years, different countries around the world, they are trying to achieve what we call carbon neutrality. And carbon neutrality means that we want to remove any source of carbon dioxide or any kind of non-environmental emissions into the atmosphere in order to try to tackle the global change, the global climate change. And digital real-time simulation for me is one of the most important tools to do this job. And to do this job, we require new simulation tools and new simulation mechanism in order to demonstrate the secure and reliable operation of this changing power system. And today I will try to use between 45 to 50 minutes for running this presentation. I will try to do my best in that short time. But before I start, I would like to introduce myself. My name is Francisco Gonzalez-Longatt. I was born in South America, in Venezuela, and during recent times, I have been involved in Norway at the University of Southeastern Norway. I spent 3 years in Norway, and during my time over there, I have the beautiful experience to develop from scratch a laboratory that is called Digital Energy System Laboratory, DEGENSYS Lab. You can find a link on internet about this DEGENSYS Lab, and you can find more information about that. But basically, it's an infrastructure. It's an infrastructure that allows you run real-time hardware in the loop simulations. And during my time in Norway, I create this lab with the idea of ensuring the resilience and the security of low carbon technologies inside the electrical power system. However, during the introduction, something that was missing about the introduction is that few months ago, to be honest, like 8 weeks ago, I came to the University of Exeter. And I am right now working at the University of Exeter, again in power system, but now I belong what we call the Center for Smart Grid. Here in the Center of a Smart Grid, again, I'm trying to do my best in order to produce a new lab. In few weeks' time, we will have a new surprise about a new lab related to real-time simulation, okay? It's my pleasure to tell you this about the University of Exeter, because right now it's one of the top-ranked universities in the UK, the sixth top-ranked university in the UK, the ninth probably in Europe. Depending of the table league that you use to rank around the world, this university belongs to the top 100 or top 150, okay? But let's go for business. What is the agenda for today? Today I will start with some basic concepts, okay? There are many misunderstandings about real-time simulation, hardware in the loop, control hardware in the loop, and so on. For that reason, I will start with very basic concepts, and then I will show you different type of simulations, because there are many confusion about what the offline simulations and the real-time simulations are. And then I will start to focus on digital simulation and power system. I will use the classical approach, that is the online simulation, in order that you understand the concepts. But then I will go for the most recent techniques, co-simulation, real-time simulation, hardware in the loop. And at the very end of this session, I will show you some cases, publications, and some experiments that we run at the different labs, and finally some closure. Let's start with general concepts. I believe everyone in this room knows about the concept of system. System is basically the integration of different components, of different sets, that or different access or elements that they are interacting between each other based on a set of rules. To be honest, the electrical power system is a system. There is a reason for the word system in electrical power system. Because the electrical power system is basically the integration of different components that they interact each other, but at the same time they have each one of them, they have an objective. That in control system, we call that the control objective. For instance, we can imagine this single line diagram here on the left-hand side, a generator, transmission line, and infinity bus. But if we look inside this single line diagram, we can identify, for instance, that the generation unit is having several subsystems. Just focusing on the generation unit, you can have the electrical machine, the rotating machine, the synchronous machine, and you can have several control loops, for instance, the governors and the APR. But each one of them is a subsystem that belongs to a very specific physical world. For instance, the electrical machine is basically an electromechanical conversion device. The steam turbine is basically a mechanical system. And for instance, if we are talking about a steam turbine, that steam turbine requires steam that is coming from a boiler and that is coming from a thermodynamic process. What I'm trying to tell you is that electrical power systems are complex for several reasons. One of them is the size of the problem. The second one is because the non-linearity of the problem. And the third one is related to the different physical components in different environments, okay? The other thing that you need to understand is that electrical power systems are dynamic systems. But a very interesting question is, what is a dynamic system? A dynamic system is not static. For that reason, that means that the states of this system change over the time. And they can change because several reasons: input signals, external perturbations, or something related with the process. But those dynamic systems, they change. And that change must be represented by some very specific mathematical description. We use the concept of a state variable. If you are in the control theory world, we use the concept of a state variable to represent that very specific dynamic performance using mathematical equations. And that is a very important point, because we need to understand that in electrical power system, because the size of the problem, because the complexity of the problem, we use simulations, modeling and simulation tools. And modeling and simulation is very, very complicated. And especially, you need to have a proper understanding about the process. In modeling and simulation, we start with a physical system, and that physical system creates an observation. And then we want to try to create a mathematical representation. That mathematical representation of the physical system is basically an abstraction. That mathematical model has two very important aspects. One of them is that typically we assume some simplifications in order to make the model realistically usable. But at the same time, there are some hypotheses that we use in order to create that mathematical model. When we have that mathematical model, we can create some equations. For instance, the Ohm's law can be transformed in a very simple linear equation, V equal R multiplied by I. And then when we have those equations, we proceed to solve those equations. And there are two very different ways to solve those equations. For instance, if we are talking about the Ohm's law, is one very simple equation, linear equation that can be solved using what we call closed form. However, when we are talking about power system dynamics, the situation is a bit more complicated. And in those cases, we need to use numerical approximation in order to solve the problem. What I'm trying to tell you is that basically, when we are talking about computational models in engineering, we need to understand that time to time we use software, and inside those software, the basic rules, the assumptions, the hypotheses, they are integrated inside the computational model. In those software, we use some inputs, use the computational model, and then we got those outputs. But what is extremely important that you understand is that when we are using computational models, we need to take care about or understand about the assumptions and the hypotheses of that model. For instance, coming back to my original example about the Ohm's law, the Ohm's law is a linear relationship, of course, very simple, is an algebraic problem that can be directly solved. But that model is only if you are considering the resistance as a concentrated or a full resistance located in a single point. There is no temperature dependence, there is no frequency dependence, and so on. What I'm trying to tell you is that this model is the most basic that you can find, and it has limitations. You cannot simulate, for instance, the integration of changes on temperature. The other thing is that typically, in some cases, we need to use computational models, but those computational models are created based on data. And when we have data, we have some measurements. One of the most important tasks and one of the most important aspects is to calibrate the model. Because we can have some very specific equation, but inside those equations we have coefficients, we have parameters, and those parameters must reflect the real physical behavior of the system. For that reason, the calibration process of one model is very important in order to make the response, the system response, to match the real data. Of course, there are a lot of uncertainties that can happen regarding the model and regarding the parameters, but we will discuss that in a bit. I usually try to bring a very interesting quote. If you have time, please read this book. This book is from George Botz and Norman Draper. And one of the very interesting phrases that he includes is, remember, all the models are grown. But the practical question is, how grown do they have to be in order to not be useful? For instance, when I say the Ohm's law is perfectly fine, applicable in a very specific range. But if we move beyond the application, the hypothesis, the assumption of that model, at that moment the model starts to be grown. But beyond that Ohm's law, I would like to go to the reality in the power system. And the reality in the power system is that the model, time to time, doesn't match the reality. For instance, here I have a screenshot about the forecasting and about the real power production in the electrical power system in Spain. As you can see over there, at very specific moment of the day, around 8 in the morning, you can see that the forecasting was around 30,275. But 3,822. But the real demand was 30,279. And at the end, there is a huge difference. There is around 534 megawatts. And that difference, to be honest, the reality is that that can be almost a small size power plant around the world. But what I'm trying to tell you is, okay, there are difference between forecasting and there are difference between forecasting and reality. But now the question is, why those differences happen? Well, because in real world, we have uncertainties. And those uncertainties are coming from many places inside the power system. Uncertainty coming from the load, for instance, the time and spatial variation coming from the customers. Generation is changing a lot. Right now we have a lot of renewables and wind speed and insolation, and the moment that they are integrated in the power system, they are changing, that create uncertainties. More complex than that is that we have many controllers inside the power system. Some of them during the time, they change the parameters, they change the characteristics, and that create uncertainties. But also faults, communication, power flow, contractual situations, and so on, that create uncertainties. And finally, the network has uncertainties coming, for instance, for observability, controllability, topology, and so on. But uncertainties can be very, very grown. In real life, in a real world, we have some uncertainty. And there are many, many situations that we are very far to have a proper forecasting. Human behavior is one of them. Terrorist attack and so on. Natural hazards like earthquakes, floods, landslide, but also accidental human actions, fires, explosions, and so on. And this last situation that I'm talking about, uncertainties, those kind of events, we call those events low probability. Because what is the probability of one earthquake? Well, depend on the location in the earth and so on, but the probability is very low. However, the impact of these kind of things is extremely high. This is what we develop one area of the reliability in electrical power system that is called resilience. But now, coming back about the modeling in power system, the modeling inside the power system is extremely simple. Everyone related with control theory must remember that there is something called differential algebraic equation. Differential algebraic equation is basically that we use two sets of equations, one set of differential equation, one set of algebraic variables, and with that we can create the representation of any dynamic system. The reality is that the equation number one on the left-hand side is the equation that you will find in many power system analysis software. But what we need to think about is, again, the modeling and simulation. If you remember on the left-hand side, this is the flow chart that I showed you a few minutes ago. And in this case, you can see simplification and a hypothesis. Well, in traditional power system, we have used the concept of time scales. Every single phenomena inside the electrical power system is represented by some time constants. And for that reason, we can create what we call time scale separations inside the different phenomena. For instance, we have the wave phenomenon like the lightning strike that is extremely, extremely fast, and we use some kind of method for simulating that. But if we are interested just in the dynamic of the synchronous machine and the interaction with the electrical power system, well, we are in what we call the rotor angle stability or the electromechanical phenomenon. What is interesting for you is that in recent times, starting on April 2020, the different type of stability in electrical power system has changed. The classical classification is rotor angle, frequency stability, and voltage stability, but in recent time, power electronic converters has integrated inside the electrical power system, and they are creating very fast transient and changing the way that the instability can be created inside the system. For that reason, in this technical report, PES-TR 77, well, we include two new forms of instability, resonance instability and converter-driven instability. Probably you are wondering why this guy is talking about this new form of instability. Because those new forms of instability, especially the converter-driven instability, is basically motivating the changes on the modeling and simulation of electrical power system. But talking about simulation of electrical power system, this time separation have defined the classical way that we have been analyzing electrical power system. The classical way that we have been analyzing electrical power system is using two different tools, what we call the RMS simulation and what we call the AMT simulation. RMS simulation is the short name for root median square simulation. And basically is the tool that we use for analyzing electromechanical processes in electrical systems. And the other tool that we use classically inside the power system analysis is for very fast phenomenon like wave phenomenon and the electromagnetic phenomenon, and that is the AMT simulation, and AMT means electromagnetic transient simulations. The electromagnetic transient simulations has been for many years in the market. In this case is a time domain simulation. time domain simulation refers that when we are solving the differential algebraic model, we are obtaining the electrical variables in a time series that represent the behavior of the electrical variable over the time. And the AMT simulation is basically characterized by the way that those time series are presented. What I'm trying to explain is that when we are solving these electromagnetic or EMT simulations, we obtain the instantaneous values. We obtain the instantaneous values for the currents, for the voltages, and so on. In other words, when we look into the time series, we get the sine wave representing voltages, currents. In this case, one of the interesting things is that we need to include the dynamic representation of all the dynamic systems. And that represents many differential equations. For that reason, the computational burden related with the ANT simulation is extremely high. And because this is a very short-term phenomenon, we need to use very small time step in order to cover the smallest time constant related to the system. These ANT simulations, they are very famous and they are used for many reasons. In the past, we used this ANT simulation for analyzing things like, for instance, a lightning strike, or over voltages, switching over voltages, or when we want to know specifically the short circuit current on the inrush current. But most recently, and this is something that I would like that you put in your mind, that AMT simulations are coming for big power system. And the reason is, if you remember, I told you the power converters are changing the way that the power system dynamic is evolving. For that reason, now the use of this AMT simulation start to be critical when we are analyzing those power electronic converters with extremely fast transient. As I said before, when we are working with AMT simulations, we need to use the dynamic of every single component. And the dynamic of every single component, that means the differential equations or the integral equations. For that reason, when we are solving the differential algebraic model, you can have an equation that is represented like the equation presented on the right-hand side. You can see the voltages A, B, C. Remember, power systems are three-phase systems, and we have currents A, B, C. But at the same time, we need to represent the whole dynamics, and we have different inductances and also resistance. On the other hand, when we are interested in slowest transient, for instance, the electromechanical processes related with the dynamic of the synchronous machine, well, we use another tool. And the classical name for that tool is RMS simulations. The RMS simulation is again a time domain simulation. And the reason again is because the electrical variables, they are represented in time series that the time is the independent variable. However, the huge difference between RMS simulations and the ANT simulation is a very interesting assumption. And the assumption is that the system can be represented by phasors. I mean, the electrical quantities can be represented by phasors. If you use phasors, that means that you can use the concept of root mean square to represent the size of those phasors or the magnitude of those phasors. And root mean square is the big name for RMS. What I am trying to tell you is that when we are solving RMS simulations, all the quantities like voltages or currents, they are represented by phasors. And if you look here on the left-hand side, I have equation that say voltage is equal J, and remember that the J represent the imaginary quantity, and then we have the inductive reactance, and following them, we have currents. RMS simulation, to be honest, is the most used study right now in electrical power system. Worldwide, there are many software using RMS simulation in order to define the power system dynamic. And the reason is because it's not so computational heavy. The second reason is because we are interested basically in the interaction between the synchronous machine and the electrical power grid. And in those cases, we can use the RMS simulation. We can assess the reaction of the generator and the controllers during short circuit using RMS values, or the frequency response, I mean, what's happened after we have the sudden disconnection of one generator, and so on. From the system representation, you can see over here on the left-hand side that the resistance, the capacitance, and the inductance, all of them, they are represented in a constant frequency frame, in other words, in phasors. And for that reason, the inductive reactance and capacitive reactance start to appear. But probably you are wondering, okay, if we are using phasors for voltages and current, where the dynamic is coming from? And the answer is that the dynamics is coming from the synchronous machine and all the controllers related to the devices inside the electrical system. For instance, here on the right-hand side, you can see a second-order differential equation, and that second-order differential equation is one way to represent the swing equation. And in this case, we are representing the electromechanical dynamics of the synchronous machine. Of course, if we include some controllers, for instance, this mechanical torque will be affected by several differential equations defined by the governor, and this electrical torque will be affected by several differential equations coming from the AVR, or automatic voltage regulation. Okay, but this is regarding the two different types of simulations that we use. However, the simulations inside electrical power system has evolved a lot over the time. I think the first attempt to model and simulate the electrical power system was using what we call analog computers. Analog computers was the first step. In 1924, in the MIT in the United States, they create the first analog computer, and then the name was transient network analyzer. The transient network analyzer was basically like a huge Lego, and you can interconnect a small transformer with small lines, and over there you can insert very small voltages and you can measure currents. What is the good part of this? Well, you can represent AC calculations in a very simple way. However, there is a lot of problems related with the TNA, or transient network analyzer. And one of them is the issue of replicating nonlinearities, replicating transients, and also if you are using lower voltages, there are many phenomena that they cannot be represented. For that reason, during the Depression after the Second World War, we start to look for some other options. And in 1940s, start to appear what we call the digital computers. Digital computers at that time, they were not so powerful, but they keep evolving. To be honest, at that moment, the utilities tried to take advantages of this and start to use the digital computers. But then the large-scale digital computers start to appear in 1950s, and that is where many of the commercial software that we have today in your laptop, in your personal computer, start to appear. However, the history of the power system simulation started in 1940s with the analog simulation. Then we start to have analog hybrids, analog and digital simulation. Then we start to have those big and huge computers, the frameworks, and custom digital simulation. The interesting part for this presentation today is the digital real-time simulation. And there are many flavors of digital real-time simulations in the market. I will tell you that the first digital real-time simulation started in Canada in what we call RTDS. RTDS Technologies Incorporated was the pioneer of the real-time power system simulation. This company was created as a spin-off of Manitoba HVDC Research Center in 1980s. And by 1989, they created the first real-time digital high-voltage current converter simulator. From there, in 1997, another Canadian company, in this case OPAL-RT Technologies, was created. The journey starting in 1997. From there, they create the first simulator that was the OP5600. To be honest, if you are familiar with real-time simulation, and I can see a few names here that they know something about that in the room, the OP5600 has been in the market for many years, and to be honest, there is a new generation of those real-time simulators, the OP5700. And one of my favorite tools is Typhoon Hill. In 2008, this company started the journey, and they start with the target of power electronics and microgrids. They were the first real-time simulator to run with time step below 1 microsecond. And basically from there are many other flavors to do more complex simulation, like the digital commercial off-shelf computers and the FPGA simulation chip. I will discuss more about hardware in a few minutes, okay? Okay, but what does mean digital simulation of power system, specifically offline simulation? Well, a simulator is basically any algorithm that we use in the computer in order to replicate the dynamic behavior. For that reason, we use digital computers to solve the differential algebraic model. However, the equation number one that you can see over there, is basically a continuous equation. When we are solving inside computers, the situation is that we need to use discrete processes. And in those discrete processes, oh, sorry, I pressed the wrong key. Oh, yes, now I am here. And we move from the equation on the top left-hand side to the top right-hand side. What I'm trying to tell you is that we are taking a time and discretizing the time and systematically solving the differential algebraic model. However, every time that we need to solve this differential algebraic model, the discretized problem, we spend time. And the problem is how long that solution take place. And in discrete time simulation, typically, if we are talking about offline simulation, the computer take the time that it's required to solve the problem. But in those offline simulations, there is a very interesting problem. Let me show you and let me explain the problem. I don't know if you can see on the right-hand side, I have two different examples. There is a line that represents the time, and that is the simulation clock. Let me use here a pointer. Let me see if you can see. This is the simulation clock, and this is the computational time. What is the difference between simulation clock and computational time? Well, this clock is representing the reality of the time, and this clock is representing the time that is spent running the calculation. But there is two possible scenarios. One scenario is that you solve the first step. I mean, for this point, you spend this time. And as you can see, you are spending less time to reach the next step. This is what we call an offline simulation that is faster than the real time. And what is the good news of this? If you have an offline simulation that is faster than the real time, well, you will get the result faster than the time that is moving in the clock. But there is the other position. The other position is that the simulation takes so much time. And in that case, you are calculating the solution for this time step. And because you take so much time, the clock is already moved on. And when you get the solution of this time step, look over here. There is a huge delay between the real clock and the solution obtained by the computer. In those cases, we call that a simulation that is slower than the real time. Okay, probably many of you are a bit confused about those concepts. What I will do is illustrate those concepts using a very simple example, okay? What I will do is show you the difference between a faster or slower simulation, offline simulation, compared in real time. If you look over here, I am using my favorite software, Dixieland Power Factory, and you can identify this is the PM Anderson 9-bus system. In this case, this is a modified version, and the idea is that I want to run a 24-hour simulation using this network, okay? And here I have a video. I am running the simulation for 24-hour AC power flow over 24 hours, okay? If I run this in real time, this must take 24 hours. But as you can see over here, I am running 24-hour simulation, a simulation for a whole day, but the total time that we spent solving this, let me move here, it was 1.13 seconds. This simulation is what we call a simulation, offline simulation, that is faster than real time. As you can see, if we run this in real time, we're supposed to have a 24-hour, but in this case, we run this in 1 second, in a bit over 1 second. But let me show you the following. In this case, I have another simulation. And in this case, this simulation represents a AMT simulation for a power converter, a short circuit on a power converter. And now I put here on the right-hand side, you can see here on the right-hand side, the real time and the simulation time. What does mean the real time? What does mean the simulation time? Real time is the real time that you have, for instance, in the clock that you are wearing on your wrist. That is the clock that is located at the wall. This is the real time. But below we have the simulation time. Simulation time is the time that is simulated inside your computer. And now the question is, could you see that for running 24 seconds of simulation, I need 47 seconds of real life? That means that this simulation, because we are using AMT simulation that is heavily computational burden, require more time, okay? But now the question is, okay, what's happened with the modern power system that they are extremely complex, nonlinear, and with different environments? For instance, right now, the electrical power system, we are in the fashion of a smart grid. We are integrating information, computation, and technologies, digital technologies, and as consequence, we have different environments. Well, the reality is that we can use a concept used in many other fields of engineering, like co-simulation. And what interesting question is, what is co-simulation? Co-simulation is basically, we have different models. For instance, one model for the electrical system, one model for the communication network, one model for the, let's say, the thermal system, and we have solvers or digital simulators for each one of those models. What I'm trying to tell you is, if I have an integrated system, like in a smart grid, that I have a very interesting communication system and electrical, I can solve them in the solver, and a master tool will integrate the solution. And that is an approach that has been in many cases, for instance, in the automobile industry and so on. What good news is that many commercial software like the Excellent Power Factory, they already include co-simulation. And co-simulation can be done in many ways. It can be using different environments, for instance, one physical layer related to the electrical grid and one cybernetic layer related to the information and communication technologies. But in this case, Power Factory allows to you combine two different electrical models. One, for instance, region 2 representing the AMT on the right-hand side, and one represented by phasors in region 1 at the bottom. And also Power Factory allow to you use many other interfaces that you can read in one of my books in order to work with different kind of digital simulations, okay? Well, now what I will do is I will show you some information now. Sorry, I pressed the wrong button. And what I would like to tell you right now is related with digital real-time simulation. Digital real-time simulation is a bit different to offline simulation. Why? Because in digital real-time simulation, we need to make that the real time, I mean the time that is running in your clock, must be identical to the time that is running your simulation. Because in this case, we want to generate and produce signals that they can be injected and they can be used inside real components. For that reason, the core of the real-time simulation is a hardware that is called the real-time simulator. And inside the real-time simulator, we have two different pieces of hardware dedicated for calculation. One of them is the classical CPU, and the other one is a novel piece of hardware that is called the FPGA. Inside any real-time simulation, we have a CPU that is typically used for solving the differential algebraic model in a relative long time scale. That time scale can be, for instance, microseconds. And then we use the very computational powerful device like the FPGA in order to solve the very time-consuming, heavily computational burden processes like the AMT simulations at the nanoscale, nanoseconds, okay? What is interesting that you understand is that this creates a huge problem, because for every single time step, we need to solve the two different pieces of hardware. The two different pieces of hardware must solve the two different parts of the problem, combine them, and provide a solution. And that is the reason that the real-time simulator is a bit expensive. What I will show you here is two of the real-time simulators that we have in the laboratory. Inside the lab, we have two different technologies. One of them is the Typhoon Hill technology, and the other one is the OPAL-RT technology. I will show you here. I opened a few years ago, I opened the OPAL-RT. In this case, this is the OPAL-RT 4510. And inside, you can see the different components. And very interesting components is that you can see at the bottom, you can see the CPU. In this case, we are talking about multi-core CPU. For instance, in this case, we are using an Intel Xeon. But also, we have here at the top the FPGA. And the FPGA is where the small time step is solved. And then we have here some digital and analog inputs. Because when we are talking about digital real-time simulation, there are basically two approaches. One of them is the fully digital real-time simulation that is basically to create models in the loop, software in the loop, and processing in the loop. And the second part, where the real-time simulation starts to be extremely powerful, that is the paradigm of hardware in the loop. In the hardware on the loop, again, there are many flavors: power hardware in the loop, control hardware in the loop, relay hardware, relay in the loop, and so on. What does mean hardware in the loop? Hardware in the loop is basically using the real-time simulation. You can see here we are running a real-time simulation inside the hardware that is the real-time simulator. But the real-time simulator has those digital and analog input-outputs that allow to interchange signals between the real-time simulator and a prototype or a computer. And that is where the real-time simulation takes off, because we can use the concept of controller hardware in the loop. In the controller hardware in the loop, we have here the real-time simulator with the CPU and the FPGA. Then we have those analog digital converters and digital to analog converters that they can send signals, low power signal for controllers like the Arduino, DSpace, or Raspberry Pi. And with this, we can create a closed loop that we call controller hardware in the loop. To be honest, controller hardware in the loop can be done very simple and very cheap. But here is where the money starts to be high, when we are using the power hardware in the loop. What is the difference between the power hardware in the loop and the control hardware in the loop? In the control hardware in the loop, the previous one, we use low power signals. We are talking about low voltages and very small currents. But when we are using power hardware in the loop, we have at the top the real-time simulator. Then we have those interfaces, analog to digital. But then we have a strong and probably very expensive power interface that is creating high currents and high voltages, and also can read high currents and high voltages. And that is where we are using the power hardware in the loop. What is the advantage of this? That you can test real devices. For instance, let me show you some examples here, and we are almost done with the presentation. One example about controller hardware in the loop is a very basic publication that we ran a few years ago. We use OPAL-RT, and inside the OPAL-RT, we include the network, or we include a model that represents a network. And that network was connected to a energy storage system, in this case, a battery energy storage system. And in this case, we want to demonstrate to the people that the controller that we were using for this battery energy storage was real and working in real time. For that reason, we use the paradigm of controller hardware in the loop. We use an Arduino Due, a very simple and very low cost single board computer. And in this microcontroller, we use MATLAB Simulink, and we put the model of our controller plus the battery energy storage. And then we run the simulation. And what was the very interesting thing here? Well, if you look here at the top right-hand side, you have the beautiful, perfect frequency signal coming from an offline simulation. You can see over there, the signal is almost perfect. It's beautiful. But if you look on the left-hand side, you can see the capture coming from the oscilloscope. And what you can see over there is similar frequency, but you can see over there, for instance, the real noise that you have in real life. One of the advantages of the controller hardware in the loop is that allows you to demonstrate concepts and real devices, hardware that can be used inside the system, okay? Okay, let me show you something about power hardware in the loop. In the power hardware in the loop, as I say we need a power conditioning or signal conditioning in order to connect to the device. In this case, I am presenting here one of the equipments that we have in the lab. In the lab, we have the real-time simulator, in this case, the Typhoon Hill 604. We have a universal Hill connect, and this universal Hill connect is interchanging signals with a physical environment. For instance, one of the examples is something that my students do at the lab. We have a network model that is inside the real-time simulator, and when we run the simulation, we can, for instance, include short circuit or faults inside the system, and we can instruct those signals to be generated and to provide it to a physical device like a relay, a protection relay. In this case, you can see that I am presenting over here a physical relay that is a cell, a Schweitzer Engineering Laboratories cell 751. And if this current represents a short circuit and the relay identifies the fault, of course, it will send back a signal opening the circuit breaker in the simulator, but at the same time, you can send digital signals using the Ethernet connectivity. Here you can see this is the physical connection between the devices, the Universal Hill Connect, the Hill 604, and the Cell 751. You can see here the real wiring, because these require a lot of wiring. And this is the network that my students are playing at the lab, okay? They got into the lab, they create the network, and at one moment they will run the simulation and they will put a short circuit. And the interesting thing is when you put the short circuit, you can see the voltages and the currents, and of course the status and the different feedback coming from the relay, okay? If you want to see more details about this, I highly suggest that you go to my YouTube channel, and in my YouTube channel, you will see a full video talking about this very specific example, okay? Well, we are almost near to close this, okay? And what I want to do right now is start with my closure. And what I want to tell you is the electrical power systems are changing a lot. Electrical power systems are not the classical power system that we have many years ago. Many years ago, we have a power system with only electrical components and nothing more than that. Right now, we have computational things, we have networking things, communication things, and at the end, the electrical power system became a cyber-physical system. And that cyber-physical system will keep moving and increasing and in that direction. And to cope with the challenges of this combination of these cyber-physical systems, the best way to solve those problems related with cyber-physical systems are basically using digital real-time simulation, okay? Well, finally, before we finish here, I always try to close and give you something that you can take and you can use. And to close my presentation today, I would like to invite you to try the virtual Hill technology. What is the virtual Hill technology? Probably many of you, some students, they are still curious about hardware in the loop, digital real-time simulation. Well, my colleagues and friends from Typhoon Hill, they have what we call a virtual machine. A virtual machine is something that allows you to emulate computational systems in your computer. And virtual Hill technology is basically a virtual machine that allows you to simulate and replicate almost everything that you face when you are doing digital real-time simulations. Of course, there are some limitations. You cannot do hardware in the loop because, of course, you are not having the real hardware because you are using a virtual machine. But you can learn and you can improve your skills regarding real-time simulation. For that reason, I include here two very interesting links. The first link at the top is related how you can get the virtual HIL device. The virtual HIL device is just a piece of software that you download and install in your computer, and you will be able to replicate and learn more about real-time simulation. But also, I highly suggest and I invite you to download and to visit the HIL Academia. Because in the HIL Academia, my colleagues and friends from Typhoon HIL, they develop courses and training for free that you can learn how to use the virtual HIL device, and also you can get some certificates and qualification if you complete the assessment. For that reason, again, my dear students and colleagues here, I highly suggest, I invite you to enroll in the HIL Academy, and also to understand the fundamentals of this. The power system is changing, and we need new generations of engineers with skills in order we cope with that. Well, it's 59 minutes in my clock, my real-time clock, and this is the end of my presentation experiences in digital real-time simulation to achieve the net zero or the carbon net neutrality. I think it's time. I hope all of you stay over here, and it's question for question and answers if you want, please.
Thank you, Dr. Francisco. It was a very wonderful session. And even myself, I am planning to incorporate real-time simulations while developing the algorithms for the power system. That's what I am trying to or planning to do in the coming future. So definitely, I'll go through your publications and go through the link and observe and see what I can do in the sector of smart grid and power system.